So, greetings, students. So we will be going into today's lecture. So, this will be the last problem of your Unit 3, and it is the continuation what we have already seen. Okay, so in the last lecture we have seen about the question and the single line diagram. So, this was your single line diagram. So over here you had two buses, bus one and this bus two. So the fault is occurring at your bus two, and apart from this, this is a PV bus, wherein it is for rated for a voltage of 11 kV, and two generators G1 and G2 are attached to this bus, and each having 10 MVA of power delivery. Okay, and apart from this, there exist two transformers, T1 and T2. And from the 11 kV bus, the voltage is stepped up to 33 kV. And again, from this 33 kV, it is stepped down to 6.6 kV. So initially, we have to find all the reactances. Okay, and this is your reactance diagram, and here is the point of occurrence of your fault, that is your F. So your F is nothing but the point of occurrence of your fault. So from the given single line diagram and the data in the question, it is possible to draw your reactance diagram. So this corresponds to your reactance diagram. Okay, so this also we have seen in the last lecture. uh, yeah, this is the given. So the base MVA they have given us 100 MVA, and the base voltage we have to consider the voltage of the bus, that is this bus. This bus we have to take as the base voltage, which is 11 kV. And from that generator reactance, we have to it's given. So generator reactance is given, and apart from that, the feeder reactance, the transformer reactance, and all we have to find. Okay, so the generator reactance, as per the question for the generator one, it is given to be 20 percentage, I think. So we have to take it to be 0.2 per unit. And with respect to the second generator, they have given around 12.5 percentage. So we have to take it around 0.125 per unit. So coming to the transformer T1, wherein your your voltage is stepped from 11 kV to 33 kV. Okay, from 11 kV it is stepped up to 33 kV. And the transformer xt1, what they have generally given is 0.1 per unit, and after that you are making a jump. Okay, so just remember with respect to the first unit, so from here to this side you'll be making a jump. So what happens when after performing the jump? So this corresponds okay, to the transformer. Next is the impedance of the transmission line after the jump. You have to consider. So over here, the old kV, the is your base voltage, which is nothing but 11 kV. So this 11 kV is substituted over here into the high voltage rating by your low voltage rating, which is nothing but your turns ratio. This corresponds to your turns ratio. So if you're taking in this perspective, means you'll be getting the base voltage to be 33 kV. So this is after the jump, that is from here to this point. So afterwards it is around 33 kV, the base voltage is changed. And next coming to this, the transmission line reactance after that jump, it is given by Z actual by your Z base. So Z actual and Z base you have to see. So Z actual you already know. Now you have to consider your Z base. Z actual is the value which is already given in the question. Okay, you have to consider the Z base. So your Z base is nothing but your base voltage square divided by base MVA. So from the given question, after the jump, will be getting the base voltage around 33 kVb square divided by your base MVA is 100. Okay, this another steps you already know in the with respect to your first unit. Okay, you just recall it. and you'll be getting the base value of as 108.9, and you have to substitute this value over here. So if you're substituting means you'll be getting the reactance for the transmission line. So the reactance will be getting around 0.055 plus J 0.918 per unit. Okay. So this is what with respect to the transmission line after the jump. That is particularly this section. This section it corresponds to this section. Okay. And next we'll be moving to the reactance of T2. Okay. And over here, that is T2 is nothing but your transformer 2. So over here, your the formula goes like this. That is your new value will be equal to your old value into your old by new voltage, the whole square by uh, new by old base MVA. Okay. So over here, the base MVA for the old value they have given around 25. So that you have to consider. But these two value remains the same. Okay, this will be 33 and this will be 33. So this gets cancelled out. So you have to solve this one and this one. So if you're solving, you'll be getting for the transformer 2, the reactance value around 0.0348 you'll be getting. After that, we'll be coming to the feeder. So feeder is also nothing but a bus. Okay, you can consider to be a bus. So for this, the thing is that you'll be again making a jump. So for feeder corresponds to this thing. So for this again we'll be making a jump. So there will be a change in the base voltage. So over here you can see it will be kV volt into high voltage rating by your low voltage rating. So that is turns ratio. This corresponds to turns ratio. So these two gets cancelled out. Okay, and this will be equal to 6.6 kV. So this will become your base MVA, and from this new base MVA, you can find your reactance. Reactance is that is for finding the reactance. It is nothing but actual by base. So for this, you have to first find the base value. So base is nothing but 6.66 whole square, and over here it will be 100. Will be 100. Okay. So this square divided by 100 will be getting, and up to this we have seen in the last lecture. Up to this we have seen in the last lecture. So after this, we have to see through the fault impedance, fault reactance. Okay. For finding the fault reactance, uh, uh, this is the ZB, and this is the reactance for the feeder. Okay, the same thing. Z actual by Z base, you'll be finding, and you'll be getting the value of ZF. And after this, only you have to find the fault current. Okay, so you will be getting all the reactances. Okay, you'll be getting all the reactances, and after this, how you'll be applying the Thevenin's theorem to find the fault current. So that's we'll be seeing. It's a very simple steps only. The already we have discussed. So first you draw the reactance diagram. Okay. So this is the particular reactance diagram. After finding the drawing the reactance diagram, you have to find the Thevenin equivalent impedance. Okay. So for that you have to see from your right side to the left side. You have to consider from your right side to left side. And over here you can see these two reactances are in parallel. You have to find the effective of this, and you have to add everything. Since it is in series, these things are in series, and this thing is in parallel. So the effective resistance for these two parallel corresponds to this value. So after this, the values which are in series are given by through this value. So which is this thing, this additive value. So this is the additive value of these four reactances. So for this, finally, you will be getting the rectangular form as 0.699 plus J 0.379. Okay, you have to convert this rectangular form into a polar form. Okay, you have to convert this rectangular form into a polar form. So if you're converting into a polar form, you'll be getting around 0.3782 at an angle of 1.1 degree. Okay, so this is what corresponding to your ZTH. So this is the Thevenin. This is the Thevenin impedance for this circuit. Okay, so we have found the Thevenin impedance, and next we have to move towards your, what you can say, you have to move towards your VTH, that is Thevenin voltage. So as per the circuit analysis, that is fault analysis part, while considering the Thevenin, I have already told that you have to consider, you have to assume the Thevenin voltage to be like a flat voltage profile, that is one at an angle of 0 degree you have to consider. So if you're considering that, means after considering, you'll be getting the VTH at 1 at an angle of 0 degree. So after this, you have to find the fault current. So fault current is nothing but your Thevenin voltage divided by your Thevenin impedance. That is VTH divided by your ZTH. So that corresponds to your fault current. And here, the Thevenin voltage is 1 at an angle of 0 degree. You have to substitute over here. And after that, ZTH is the value what we have found in the previous slide. So that value you have to substitute over here. So if you are substituting, okay, this one you will be taking the reciprocal. You will be taking the reciprocal of this to get the value of 2.644, and the angle just gets jump over from your denominator to the numerator to the value of minus 1.1 degree. Okay, so this corresponds to a fault current. And next is your base current. So why we had to go find the base current in the sense, the fault current what we have found is in terms of your per unit. You have to consider the unit. Okay, the fault current what we have found is in per unit representation. So in order to change from the per unit representation 2 amperes to the SI unit ampere, you have to multiply this value with your base current IB. Okay, we are, for not to get the value of your fault current in amps, that is your SI unit, you have to multiply this fault current in terms of your base current, that is IB. I hope you are clear. So for that you have to find the IB, that is the base current. Okay, so you'll be getting KVAB divided by root 3 into KVB. So this is your voltage at your old. Okay, I'm having a particular doubt over here. Okay, so here it is nothing but power, apparent power, but over here they are substituting in terms of KVAB, and they are substituting 10 into 1000. Base MVA. Okay, okay, they have considered your they have considered your KVAB. Okay, I will be checking through that, and I'll be telling with respect to this. And apart from this, if you are substituting this 10 into 1000, you'll be getting the value of around 874.77. So now that is your base MVA. So the base current. So for the base current, we'll be multiplying with respect to the value what we have found in terms of per unit. Okay, that's what over here it is done in order to get your final IF. Okay, this is the value. and the final fault current will be 2.313 at an angle of minus 1.1 degree kiloamps. Okay, so you might be asking, sir, whether it is possible to go for the current in terms of kiloamps. It is possible in your transmission line. Okay, in your transmission line, it is possible, but uh, it is determined by the occurrence or the position where the fault occurs. Okay, so now we are currently speaking about fault current. So the fault current can be large up to this. So just imagine. So even for a current flow of 1 amps, there is a drastic effect. Okay, if even 1 amps flows within our body, there will be a drastic effect and it causes some severe damages. But just imagine here the fault current which is occurring over the transmission line, it is around 2.313 kiloamps, not even in amps. So it is represented in kiloamps. So, so that is the severity in the power system network. Okay, when the fault occurs. So at any cost, the power system network engineers will try to avoid this fault current. Okay, so that's what with respect to this problem. And as I said, there's a particular doubt I'm having with respect to the base current IB, and I will be clearing it to you. Okay. Okay. So with respect to this, your third unit gets over, and I'll be putting the assignment today, and I'll putting the submission date also soon. So try to complete the assignment.
Sir, can you give 1 week time, sir?
Yeah, sure, sure. I'll be giving a lot of time. So don't worry. That too, I'll be giving most of the problems from the notes, so it will be easy for you. So it will be easy for you in your hectic schedule. Okay. So most of the problem I'll be giving from your notes. Might be one or two from the book. If possible, I'll be giving. Okay. So you can just balance your workload. Okay. And I think I'll be stopping with this. I'm also having lab today.